Welcome everybody once again. So this is our fourth module and part 3. We are studying Kanis method. In the first class we saw the basics of Kanis method and how to analyze indeterminate structures using Kanis method. We saw the welcome everybody once again. In the second class we saw one example. This is our how to analyze a three-span continuous beam with and part 3. We are studying Kanis methods. So this is our in the first class. Second we saw the basics of Kanis method of this problem from the previous problem is indeterminate structures using Kanis method. The moment of inertia, the loading conditions, in everything the second class we saw one example. The only difference how to analyze a three-span continuous beam with the are hinged here. The end supports are hinged or simply supported. So in the previous problem, the end second example fixed. So the difference of this problem from the previous problem using Kanis. See the span length. So your problem is you the have moment of inertia, the loading conditions, everything is the same. The only span AB you have the end UDL of 2 kilonewton per meter. The end supports are hinged. The span or BC we have 8. In the previous problem, Newton concentrated load acting at a distance of 3 meters from B. How will you analyze in the span CD? We have an 8 kilonewton load. So your problem is you have at a distance of 2.5 meter from C or D. That is, it is acting at in the span AB. You have the moment of inertia UDL of 2 kilonewton per meter. For the span BC is 2 in the span BC we have 8. Sorry, we have 5 kilonewton concentrated load acting at a distance of 3 meter from B and 5 meter for in the span CD we have an 8 kilonewton load acting at a distance of 2.5 meter from C or D. That is, it is acting as usual. Our first step the moment of inertia for the span AB is I. For the determination is 2I and for the span CD is I. So step 1 we will find span length is 6 meter for AB, 5 meter for BC and 5 meter for C. So how will we solve such already how to find the fixed end moments? Step 1. For the span AB, so as usual, our first step is to find so you have to consider all the supports as fixed end moments. So A and step B 1 we will find the fixed support, fixed and when you are taking a section, we know the left anti-clockwise is positive and the right we know already how to find the fixed end negative and right for the span AB. When you are considering the span AB, see that means so you have to consider fixed supports all the supports as fixed moments. So A and B are considered as fixed support. So and when you are taking a section, we know the left anti-clockwise is positive and the right clockwise is positive. In order to show anti-clockwise is negative and right anti-clockwise is UDL. Our fixed end moment will be fixed in the M half AB will be equal to minus WL square by 12 and M of BA will be equal to plus WL square by negative and the right fixed end moment is taken as positive. So we will find M of AB and M of clockwise and clockwise. And since it is UDL, our fixed end moment will be in the MFAB will be equal to minus WL square so by 12 MF and M of BA will be equal to plus WL square minus WL square by 12. So we will find M of AB and M of B 2 into 6 square divided by 12. So that is equal to minus 6 kilonewton meter. So our similarly AB will be equal to minus WL plus WL square by 12. So we get minus 2 plus 2 into 6 square divided by 12. So that is equal to plus 6 kilonewton meter. Minus 6 kilonewton. Now we will move on to the span BC. Similarly, so while you are considering the span BC, BA will be equal to for fixed end moment. The support WL square by 12 as fixed support. We have so plus 5 kilonewton when you are taking a section divided by 12. Anti-clockwise so is negative and the right clockwise is negative. That is hogging moments. Now we will move on to left it is minus and the right so while you are considering the span BC. So the fixed end moment W support is concentrated load W should be considered as fixed support. AB so there is 5 kilonewton. When you are taking a section, the left anti-clockwise is negative and the right clockwise is negative. So that is hogging moment. We will use this formula so to find M minus and the right it will be plus. So the formula is W, since it is concentrated load, W AB square by, so our MFBC is equal to
L square
minus WAB square by L square.
We will use this formula to find
MFBC and MF 5 into 3 into 2 square divided by 5 square. We get minus 2.4 kilonewton meter. So our MFBC is equal to minus WAB square by L square. So that plus is equal to minus square B by L square. 3 into we get plus square divided by 5 square. 3 square into 2.4 kilonewton. 5 square kilonewton meter. We get plus 3.6 kilonewton meter. MF
now we
CB
will consider
will
the
be
span
equal to
CD.
plus
So while
WA
considering the span
square
CD,
B by
you have
L
to
square.
consider both
We get plus
C
the 5
and DS
into
fixed support. We have
3 square
8
into
kilonewton
2
load
by
at the midspan.
5 square.
2.5. We get, so
Plus
here it is
3.6
left anti-clockwise is negative
kilonewton
and right clockwise is
Now
negative.
we will consider the
So
span
this is
CD.
you will get plus minus
So while
sign, and for
considering the
clockwise
spans
you will give plus
BCD,
sign.
you have to consider
Both support
now
C
the
and
formula
DS
will
fixed
be
support.
minus
We have
W,
a
here
8
A is
kilonewton load
AB
acting
square
at the
by L
midspan,
square.
2.5,
So minus
2.5.
W into A will be L
So
by
here
2
it is
and
left
B will
anti-clockwise
be
is
L by 2.
negative
So
and
L
right
square
clockwise
by
is
4
negative.
into L square. So you will get minus
plus
W
minus
L by
sign, and for
8
clockwise
and
you will
for
give
M
plus
of
sign.
BC you will get plus W L by 8. Now the formula will be minus W, here A is AB square by L square. So minus W into A will be L by 2 and B will be L by 2. So L square by 4 into L square. So you will get minus W L by 8. And for MFBC you will get plus W L minus W L by 8. So you get minus 8 into 5 by 8. That is minus 5 kilonewton meter. Similarly, MF DC will be equal to plus WL by 8.
CD
So
will
that
be
is
equal
equal
to
to
plus
minus
8 into
W
5
by 8. We will get
L by 8
plus 5 kilonewton. So you
meter.
get minus
So first
8
step, normally
into 5 by 8.
complete
That is
our
minus
first step with
5
this.
kilonewton
So
meter.
here it is
Similarly,
not completed. We have to do one more step.
DC will be equal to plus WL by 8.
See, we have
So that is
already
equal to
studied in
plus
our moment
8 into 5
distribution
by
method.
8. We will
When
get
the end
plus
supports
5
are simple
kilonewton
or
meter.
hinged support.
So first
we
step,
will normally we will complete our first step with this.
Right?
We
So
will balance
here
the moment.
it is not completed. We have to do one more step. Because the end supports
and
are
we will release the
support.
moment.
See, we have already studied in our moment distribution method when the
symbol
end supports are
to the
symbol or
neighboring
support
to the nearest
we will so here the extreme
balance
support,
the
the end
moment.
supports A is
Right?
symbol
We will
support,
balance the moment.
D is symbol support. So since A and D are symbol supports, we know moment
And we
at
will
A will be
release
equal
the
to
moment
0 and moment
from
at D
A,
will be equal
that is
to
from
0.
the
But since we have
symbol
determined
support
fixed end
to the
moments,
neighboring
these
support,
moments,
to the
that
nearest
is
support.
M,
So
A,
here
B
the
should be
extreme
transferred.
supports
The
to the
end
joint
supports
B,
A is
and
symbol
M of
support,
DC
D
should
is
be
symbol support.
released
So
to
since A and D are
joint
symbol
C.
supports, we know moment
So
at A
fixed
will be
end
equal
moment
to
at
0
A
and
should be
moment
released
at
to
D will be
joint P,
equal
and
to
fixed end
0.
moment at D should be
But
released
since
to
we have
joint
determined
C.
fixed end moments,
So that is called
these
the modified
moments, that is
moments.
M,
Modified
A,
B
fixed
should
end
be
moments.
transferred to the
So
joint
now
B,
we have to
and M of
write
DC
the modified
should be
fixed end moments
released to joint C.
Okay.
So fixed end moment
So how
at
will we
A
modify
should be
the
released
fixed
to
end moments?
joint B, and
We will
fixed end moment at
release
D should be released
this,
to
the
joint
M of AB.
C. So
At
that
A,
is called
we have
the
minus
modified
6
moments.
kilonewton.
Modified fixed
So
end moments.
releasing.
So
now
balancing
we have to
and releasing this
write
minus
the modified
6 becomes
fixed end moments
plus 6. And half of this minus 6 will be transferred
So how will
to
we
the
modify the fixed end moments? We will release
nearer support or the neighboring support.
See M of AB. So
at A we have minus 6 kilonewton. So
this
releasing,
M of B,
so
A
balancing
becomes.
and releasing,
So modified
this
fixed
minus
end moment
6
M
becomes
of
plus
BA.
6. So we are
and half
balancing
of
this minus 6.
So
will
M
be
of AB
transferred to
becomes
the
0
while balancing
nearer
this
support
becomes
of the
0.
neighboring support.
And
So,
half of this is transferred to the neighboring
M
joint
of
B.
BA becomes.
Okay.
So modified fixed
So that
end moment.
means
See, when
M
you are
of
considering the span
BA.
AB.
So we are
AB,
balancing this.
B is
So M
the
of
intermediate
AB
support.
becomes
B
0.
is intermediate support.
While balancing this
A
becomes
is
0.
the extreme symbol support.
And half
So,
of this
A you have
is
minus
transferred to the neighboring joint B.
So this minus 6 should be balanced.
So that
So you
means,
have
see,
to
when
give
you are
plus
considering
6,
the span
and
AB,
after balancing half
AB,
of this plus 6 is
B
transferred
is
to
the intermediate
BA.
support.
B
That
is
is
intermediate
half of
support.
6 is A is 3.
The extreme
So 3
symbol
kilonewton meter
support.
is
So
transferred
A
to
you have minus
the
6
joint B. Kilonewton meter.
So what you
this
get
minus
is
6 should be balanced.
M
So
of
you have to
BA
give
will
plus
be
6.
equal to,
And after balancing, half of this plus 6 is transferred to, see,
BA.
already you have one
That
plus
is
6.
half of 6
So
is
plus 6, 3. So
plus
3 kilonewton meter is transferred
half
to
of
the joint
6
B.
by 6.
So what you get is M of BA will be equal to, okay, that is this 6. This 6 is balanced so that you will be giving plus 6. See, already you have 1 plus 6. So you get
6
9 kilonewton meter plus 9 kilonewton meter
half
as M
of
of BA. Similarly,
6 by 6
at D, from D, okay, that is this 6. See,
the
balancing
balanced
so that you will be giving plus 6. So balancing you will get minus 5. So you get, so half of 9 kilonewton meter
minus
9 kilonewton meter
should be transferred to this joint.
Similarly,
2.5 should be transferred to this
at
joint.
D. So what we get is M of CD will
From
be equal
D,
to, M of CD will be equal
balancing
to minus
M of
5.
BC is plus 5.
From here
So
you
balancing
balancing
you will get minus 5.
So half of that,
So
it
half
is minus
of this
2.5.
minus
2.5 should be transferred to this joint.
We get
minus 7.5 kilonewton meter. So what we get is M of CD will be equal to, so this M of CD will be equal to minus 5.
F DC
From here you
becomes
balance,
0.
you get minus 5. So half of that,
M of
it is
AB
minus
becomes 0.
2.5.
And the remaining
moments remains the same. M of BC
we get
and M
minus
of CB remains the same.
7.5
So M of
kilonewton meter.
BC is minus 2.4 kilonewton meter. So this M and M of CB DC becomes 0. Is 3.6. So M of AB becomes
This
0.
remains the same.
And the remaining moments remains
so you
the
should
same.
be very
M of
careful
BC
while
and M of CB remains
writing
the
the
same.
fixed end moments
So
in
M
the
of
Kanis
BC is
method,
minus 2.4
because the first step
meter.
itself, depending upon the end conditions, you have to
And
write the
M of
modified fixed
CB
end moments also.
Is
Now we will move on to our
3.6
second step.
kilonewton meter.
Second
This
step
remains
is
the same.
determination of rotational
Okay,
factors.
so you should be very careful while writing the fixed end
So our
moments in
step
the
2
Kanis method, because the first
you
step
have to
itself,
find the
depending upon the
rotational
end
factors.
conditions, you have to write the modified
So
fixed
we
end
know
moments
rotational
also.
factor
is equal to minus
Now we will move on to
half
our
of
second step.
the
Second
distribution
step is
factors.
determination of
So
rotational
first
factors.
of all, we will consider the joints.
Okay.
We have two intermediate joints B
So
and
our
C.
step 2,
that is two joints where more than one member
we have to
acts.
find
So
the
at the joint
rotational
B,
factors.
we have the member BA. So we know
And
rotational
BC.
factor is equal
At joint
to
C, we
minus
have the member
half of
CB and
the
CB.
distribution factor.
You can see from the
So
diagram.
first of all, we will consider the
At
joints.
B, we have the members
two
BA,
intermediate joints B and C.
BA
That
and
is two
BC.
joints.
At C,
where
we
more
have
than
CB
one
and
member
CB.
acts. So at joint
Now,
B, we have the member BA.
we know the relative
and BC.
stiffness. If the
At
far
joint
end
C,
is
we
fixed,
have
the
relative
member
stiffness is
CB
taken as
and
I by
CB.
L. And if
You
the
can
far end
see
is
from the
hinged, the
diagram.
relative stiffness is taken as
At
3 by
B,
4
we
I
have
by
the
L.
members BA.
Okay.
BA
So here
and
B and C are
At C, we
intermediate
have
supports.
CB
So B
and
and C should be considered as
Now,
fixed supports. Intermediate supports are
we know
assumed
the
to be
relative
fixed supports.
stiffness. If the
Because
far
there
end
will
is
be
fixed,
the relative
negative
stiffness
moments.
is taken as I by
Fogging
L.
moments.
And if the far end is
At
hinged,
A
the
and
relative
D.
stiffness
See,
is
A
taken
and
as
D are
3 by
hinged
4 I
support
by L.
or symbol supports.
Okay,
So
and
here B and C are intermediate
supports
supports.
or hinged
So B
supports.
and C should
B
be
and C are
considered as
intermediate
fixed
supports.
supports.
They will be considered
Intermediate
as
supports are
fixed
assumed to be
supports.
fixed supports because there will be
So now,
negative moments, hogging moments.
at A and D, see A and D
So
are
after writing
hinged
the
support or
joins, so
simple
these are the
supports.
members.
A and D will be considered as
So after
simple
writing the
supports
members,
or
we will
hinged
find the
supports.
relative
B and C are
stiffness.
intermediate supports. They will be considered as
Relative
fixed
stiffness
supports.
is represented by small
So
k.
now, so the relative stiffness BA, the far end is hinged.
So after
That is,
writing the
A is
joins,
hinged.
so these are the
A is a simple
members.
support, so it is hinged. So we get 3 by 4
So after
of
writing the
I
members,
by
we will
L.
find the relative stiffness.
So that is nothing but 3 by 4 of
relative
I is
stiffness
I,
is represented by
L is
small
6
k.
meter. So the
Now,
relative stiffness
for the
BA,
span
the
BC,
far end is hinged. That is, A is hinged. A is a simple support, so it is hinged. So we get 3 by 4 of I by L. So that is nothing but 3 by 4 of,
for
I
BC,
is I,
for the member BC,
L is 6
C
meter.
is intermediate support, so it should be considered as fixed
Now,
support.
for the
So
span
it is I by
BC,
L.
so BC, for the span BC, I is, actually it is 2I. So I should be replaced by 2I divided by L
for
is
the
5.
member BC. C is
Now for the
intermediate
span
support,
CB,
so it
far
should be
end is
considered as
B,
fixed
B
support.
is
So it is I by L.
intermediate support, it should be considered as
BC
fixed
for the
support.
span
So
BC,
I by L, I
for
is,
the span BC or
actually it
CD,
is 2I.
I is 2I, so 2I divided by 5.
So I should
For
be
the span
replaced by
CD,
2I
D is
divided by L
far
is
end
5.
is symbol support. So it is 3
Now
by
for the
4
span
of I
CB,
by L.
far end is
So
B,
3 by 4
B
of
is
I is I and
intermediate
L is
support, it should
5.
be considered as fixed support.
So now we will
I
take
by
the sum.
L.
For the span BC or CB,
Sum,
I
that
is
is sigma
2I,
k.
so 2I divided by 5.
So sum, it
For
is
the span
3I
CD,
by
D is the
24
far end
plus 2I
is
by 5,
single support.
we get
So it is 3 by 4
63I
of I by L.
by 120.
So 3 by 4 of I is I and L
2I
is
by 5 plus 3I
So
by
now
20,
we will take the
we
sum.
get 11I by 20.
Sum, that is sigma k.
Now
So
we
sum,
will find
it
the
is
distribution
3I
factor
by 24
plus 2I by 5, we get
So distribution
63I
factor is
by 120.
K by sigma k. Relative stiffness
2I
by
by
summation
5
of the relative
plus
stiffness.
3I by
So it
20,
is 3I
we
by
get 11I
24
by 20. Divided by 63I by 120, we get, now we will find the distribution
5 by
factor.
21.
Now 2I by 5 divided by
distribution
63I
factor
by
is
120, we
K
get
by sigma k.
16 by
Relative
21.
stiffness by summation
So
of
you
the
add
relative
these
stiffness.
both, we should get 1.
So it is
5 by
3I
21
by
plus 16 by
24
21
divided by
is equal
63
to 63I by 120. We
Now,
get
at joint C,
5
by
by
member
21.
CB, the distribution factor is 2I by 5
Now
divided
2I
by
11I
5
by
divided
20,
by
we
63
get 8 by 120,
8 by 11.
we get
And
16 by
for the
21.
member CD, 3
So
I
you
by
add these
20
both, we should get 1. 5 by 21 plus
divided
16
by
by
11
21
I
is
by
equal
20,
to 1.
we get 3 by 11. So when
Now,
we add, we get 1.
At joint C, now
For
we
the
will
member
determine the
CB, the
distribution
factor is
sorry,
2I by
rotational
5 divided by
factors.
11I by
So
20.
rotational factor is
We
equal
get
to
8
minus
by
half
11
of the distribution
and
factor.
for the member
So 5
CD,
by
3I
21
by
into
20
minus 0.5
divided by
get
11I by
minus
20,
0.1
by
11.
11. So when we
Now
add,
for
we
the
get
member
1.
BC, it is a 16 by 21
Now
into
we will determine the
minus
distribution
0.5.
rotational
We get minus
factors.
0.381.
So rotational factor is equal to minus half
Now for
of
the
the
member
distribution
CB,
factor.
it is 8 by 11
So 5 by
multiplied by
21
minus
into
0.5
minus
we
0
get minus
0.5. We get
0.364
minus
and for the member
0.119.
CD 3 by 11
Now for the
multiplied
member
by
BC,
minus
it is a 16 by 21 into
minus
minus
0.5, we get minus 0.3. So step 2 rotational factor is completed. Now for the member
step
CB,
3 we will
it is
find
8 by 11 multiplied by minus
restrained
0.5,
moments.
we get minus 0.364. And
So
for
the
step
member
3, 3 by 11 multiplied by minus 0.5, we get minus 0.136.
Is resultant.
So step 2 rotational factor is completed.
Restraint
Now step
moments.
3 we will find the resultant restrained moments. So we know the resultant restrained moments is the summation of step 3, the moments of all the members joining at a joint, meeting at a joint. So the equation is MFI is equal to sigma j of moments, MFIJ. So here we know the resultant restrained moments is the summation of two the moments of all the members joining B at a joint and M of C at a joint C. So the equation is MF the members, the fixed end member, fixed end MFIJ of the members meeting at joint here we have the intermediate joints as B and C. So we have two MF restrained moments, MFB at joint B and MF C at joint C. So at joint C, the members are the fixed end moments joining at fixed member joining at the end moments. Joint C are of the members meeting at joint B are MFBA CD plus MF. So at B, C, we have MFBA plus MFBC. C. At C, at joined C, we have MFCB, the fixed end moments joining at CD. The member joining at the joined C here we have to take the modified fixed end moments plus M so modified fixed end moments. M of BA so at 9. M of BC we have M of BA plus M of BC. So it is 9 C, minus 2.4 we have M of CB plus M of at joined C it is M of CB plus M of CD. So plus here we have to take the modified fixed end moments. We get minus 3. So modified fixed end moments. M of BA is 9. So this M of BC is 9 minus 2.4 plus M of BC minus 2.4 we get plus 6.6. So minus 2.4 M of CB plus M of CD 6.6 kilonewton minus 7.5. Now we get M minus 3.9 3.6. M of CD is minus M of 7.5 is 9. We get minus M of 3.9 minus kilonewton meter. So minus 2.4 we get plus 6.6 kilonewton meter. Now M of we will enter these values. These values in the Kanis CD is minus 7.5. We get minus 3.9 kilonewton meter. So we have two joints. So we will draw the smaller box for B. Now we will enter these values. First of all, these values in the Kanis for joint B, we have one smaller box and one larger box in the smaller boxes. So we have two joints for joint B. So we will draw the smaller joint C. We have one smaller box. B. See first of all one larger box. For joint B, we have one smaller C, box, right? B and C, and one larger box are intermediate members. And here we have joint B, member A. For and joint C, we have one smaller box. And one larger box. So A is one support. This is joint C, right? B and C. B is another support. C are is intermediate members. And here we have and D is another support. Member A. Now in the smaller boxes we have to write joint the restrained moments. So MFB is so plus A is 6.6. We will write plus 6.6. MFB is another support. Is minus 3.9. We will write minus 3.9. And D is now we will write another fixed end moments. Now in the smaller boxes we have to write the modified fixed end moments. It is a 0 so for AB it is 0 plus 6. BA it is 9. We will write plus 6.6. MFC so is minus 3.9. We will write minus 3.9. Plus now we will write the fixed end moments for BA. So we know BC that is the modified fixed end moments. It is a 0 for AB. It is a 0. For BC it is minus 2.4 and for CB it is plus 3.6. So modified fixed end moments are 0, minus 2.4 and plus 3.6 for BA. Now for CD,
BC and CD.
CD it is minus 7.5 and for DC it is 0.
For BC it is minus 2.4.
So minus
CB it is plus
7.5 and for DC it is 0. So actually these are the modified
minus
fixed end moments.
2.4
and plus 3.6. Now we will
for
write the
CD,
rotation factors at a joint
CD
B.
it is minus
We have the members
7.5
BA
and for
and
DC
BC
it is
0. So the rotation factors are minus 0.119
So minus
and minus
7.5
and for DC it is 0. So actually
So we
these
will
are
write
the
the rotation
modified
factors.
fixed end moments. The rotation factors are minus
0.119.
Now we will write the rotation factors at a joint B. We have the members
and
BA
minus
and BC. So the rotation factors are minus 0.119 and minus 0.381.
So we will
Now
write
at
the
the joint
rotation
C,
factors.
the rotation factors are minus 0.364 and minus 0.136. 0.119, 0.119.
So at
C, the
and
rotation
minus
factors are minus
0.381.
0.364.
364.
Now at the joint
And
C, the
minus
rotation factors are minus 0.364 and minus
0.36.
0.136.
Now we have to find
So at the
rotational
C, the
contributions
rotation factors are
of each joint.
minus
Rotational
0. contributions. So these rotational contributions
364.
are represented by
364
small
and
m.
minus
0.
So
small m 1 AB
6.
small m BA.
Now we have to find the rotational contributions of
Capital
each
AB.
joint.
Here small m
contributions.
BC.
So these rotational
small
contributions
m
are
CB
represented
small
by
m CD
small
and small m
D.
So small m
So
AB
A and D are
small
extreme
m
supports.
BA. We have already released. We have already balanced and released these moments to B. So here we do not have any. Here small
Moments.
m
So we
BC.
have the iterations, right?
Small
So this
m
is
CB,
iteration 1.
small m CD,
We will
and
go
small
for 5
m
iterations.
B. So iteration 2, iteration 3.
So A and
iteration
D
4
are extreme supports. We have
and
already
iteration
released.
5. We have already balanced and released these moments to B. So here we do not have any moments. So we have the iterations, right? So this is iteration 1.
So for the first iteration,
we will go for 5 iterations. So iteration 2, iteration 3.
we will find MCB.
Iteration
We will
4.
start from MCB first.
And
so
initially we
5.
will assume MBC as a 0. See, only the contribution is from MCB to joint B and from MBC to joint C. I repeat, the rotational
So for the
contributions
first iteration,
are from MCB to joint B and this MBC to
we will
joint
find
C.
MCB. We will start from MCB
So we
first.
know the formula.
So initially we will
how
assume
to calculate.
MBC
So first
as
of all
a
we will
0.
calculate MCB.
See, only the contribution
then we
is
will calculate
from
MCD
to joint
then we will
B
calculate MBC
and from MBC
and then we go for
to joint
MBA.
C.
I repeat,
So
the
these
rotational
are called
contributions
Kanis
are from
iteration
MCB
cycles.
to joint
So
B
that will be
and this
our
MBC to joint. So this
C.
is our step 3. So we
So
know
step
the
4,
formula how to calculate. So first of all we will calculate
is
MCB,
Kanis
then we will
iteration
calculate
cycle.
MCD, then we will calculate MBC and then we go for MBA. So these are called Kanis iteration cycle. So step 5 we will go for iterations. We have drawn the iteration cycle. So this is our step 3. So step 4 we will go for the iterations. Is Kanis iteration cycle. So iteration 1, right? So step 5 we will go for iterations. We have drawn the iteration cycles. So step 5 we will go for the iterations. Previous problem I told you, I explained you in detail. So here, iteration 1, right? We will open a tabular column and we will do it in a very simple manner. So each time we are not going to write the equations. So iterations, totally 5 iterations, right? So 1, 2, 3. See, previous
4,
problem I told you,
5.
I explained you in detail. So first of all we will calculate MCB. So here We will do it in
we know the formula.
We will open a tabular
MCB
column
is
and we will
equal
do it
to
in a very simple manner. So each time we are not
rotation
going to write the equations.
factor of
So
CB.
iterations, totally 5 iterations, right? So
Multiplied
1
by
2, 3, M,
4,
F, C.
5.
That is which is written
So
in the
first of
smaller
all,
box.
we will calculate
MCB
plus.
So we know the
how
formula
much
the
MCB
nearer
is
joint is
equal to
contributing, that is MBC.
rotation factor
MBC
of CB.
right? Multiplied by, so then we will calculate MCD. So MCD will be equal
that
to,
is
which is written in the smaller box,
RCD.
M of C,
That is rotation
plus
factor of CD.
how much the nearer
multiplied by
joint is contributing, that is
same thing,
MBC.
MFC plus MBC.
MBC, right?
Then
After calculating MCD, we will calculate.
So
then we will
MBC.
calculate MCD. So MCD will be equal to MBC is equal to rotational factor of BC multiplied by
same
the
thing,
restraint
MFC
moment. Plus
that is
MFB plus
Then
small m.
after
So the
calculating
MCD, we will calculate
contributing
MBC.
rotational contribution is from MCB.
MCB. So MBC is equal to rotational factor of BC multiplied
Now
by,
we will
find MBA.
The restraint
So
moment.
MBA is equal to rotational
That is
factor of
MFB
BA multiplied by
plus
small
same.
m of
So
B
the
plus MCB.
contributing rotational contribution is from MCB.
So, see, initially
MCB.
we will assume this. For the first iteration, we will assume MBC is equal to 0.
BC.
Okay. Now we will find MBA.
Okay.
So MBA is equal to rotational factor of BA multiplied by same M of B plus MCB. So, see, initially we will assume this. For the first iteration, we will assume MBC is equal to 0. Okay. So for the first time, see, for calculating this RCB, always RCB is the same, right? RCB is minus 0.364. That is not going to change. Minus 0.364. RCB is minus 0.364. That is rotational factor. Multiplied by MFC. MFC is minus 3.9.
So for the first time,
plus
for
calculating this,
so for the first
RCB,
iteration, we
always
will
RCB is the same, right? RCB
we will
is
get
minus
the value as
0.364. That
plus
is not going to change. Minus 0.364. RCB is minus 0.364.
MCD
That is
is equal
rotational
to
factor.
RCD.
Multiplied
RCD
by
is
MFC.
minus
MFC is minus
0.136
3.9
multiplied by
plus
MFC
MBC.
is minus
So for the first iteration, we will assume
for the first
MBC
iteration,
is
we will
equal to
assume
0.
MBC is
So
0.
we will get the value
get
as
plus
0.5020. Now, we are going to find MBC,
MCD
right?
is equal to RCD.
RCD is
MBC
minus 0.136 multiplied
So
by
MBC is
MFC
equal
is
to
minus
RBC.
3.9.
RBC is
So
minus
for the first iteration, we will assume
MBC is
minus
0.
0.381
We get
multiplied by
0.530.
restrained moment, that is plus 6.6.
Now,
We are going to find
multiplied by plus
MBC,
6.6
right? Plus MCB. So
This
MCB we have already
MBC.
found. It has 1.420. So you have to use this
MBC is equal to
1.420.
RBC. RBC
So we
is
get
minus
0.381.
minus
0.381 multiplied by, this is the restrained factor.
Now,
Restrained
MBA.
moment, that is plus
So BA
6.6.
is here, right?
Multiplied by
MBA.
plus 6.6.
So
plus
MBA is
MCB.
equal
So
to
MCB we have
RBA.
already
RBA
found.
is minus
It has 1.420
0.119
multiplied
you have
by
to use this
1.420.
MFB is
So
plus
we get
6.6
plus MCB.
minus
MCB we have calculated it as plus 1.420.
So we
Now
get
MBA.
minus
So BA is here, right? MBA.
9.
So
5,
MBA
4.
is equal to RBA. RBA is minus 0.119 multiplied by MFB.
See, since
MFB is plus
I don't have place
6.6
here, I have told you
plus
the values.
MCB.
Okay, you have to
MCB
substitute
we
and
have
you can
calculated
find
it as plus
or minus,
1.420. So now
So
we
we
will
get
write the first
minus
iteration, results of the first
0.954.
iteration. That is MCB. MCB is plus 1.420. MCD is
since
plus 0.530.
I don't have place here, I have told you the values.
MBC
Okay, you
is
have to substitute
minus
and you can find it as plus or minus, etc.
So now we will
6,
write the
MBA
first
is minus
iteration, results of the first
0.934.
iteration,
minus
that is
0.954.
MCB is
Now
plus
we will move on to our second iteration.
1.420.
Second iteration.
MCD is, so for the second
plus
iteration, the formula
0.530.
remains the same. MBC is, the
Minus
formula remains the same.
3.0.
Only difference is the change in this MBC.
And MBA is
Now,
minus
for this
0.954.
MBC, you have
Minus
to use this value. That is
0.954.
minus 0.
Now we will move on to our second
All
iteration.
the remaining things remains
Second
the same.
iteration. Okay.
So
RCB
for
is
the
the
second
same,
iteration,
MFCB,
the formula
MFC
remains
is
the
the
same.
same. Only changes MBC. You have
The
to use
formula
MBC
remains the
is
same.
equal to what
Only
you have found
difference
at the
is the
last. That
change
is
in
minus
this MBC.
3.056.
Now, for
So,
this MBC,
for the second
you have to
iteration,
use
we
this
get
value.
MCB
That is
as
minus 0.356. All the remaining things
2.532
remains the same. Now,
RCB
MBC,
is the
you
same,
have to use
MFCB,
minus
MFC is the same.
3.05.
Only changes
See, in
MBC.
throughout
You
the
have to use
iterations,
MBC is equal to what you have
R
found at the
remains
last.
the
That is
same,
minus
capital M remains the
3.056.
same. Only this
So,
M, small
for the
m
second
changes.
iteration, we get MCB as
Okay, so the second
plus
iteration for these two cases, you have to use
2.
this value. Now MBC, you have
Now
to use
for these columns,
minus
you have to use
3.056.
MCB.
See,
So
in
MCB
throughout
you have
the
to use
iterations,
this value.
R
See,
remains
whatever
the
you have
same,
found
capital
at
M
the
remains the
end.
same. Only
Last
this
you have to
M,
use it.
small m changes.
So MCD you get it as
okay, so the
plus
second iteration for these two cases, you
0.946.
have to use this
MBC.
value. Now MCB, you have
Now
to use
for
RBC
these columns,
and the
you have
capital
to
MFB
use
remains the
MCB.
same.
So MCB
For
you
small
have to use this
MCB,
value.
you have to use, see, whatever you
plus
have found at the
2.532.
end, you have to use this
Last
value.
you have
Plus
to use it.
2.532.
So MCD
So
you get it as
plus
minus
0.9469. MBC. Now MCB, you have to use RBC and the capital MFB remains the same. For
So we will
small
write the
MCB,
values
you
here.
have to use plus 2.532. You have to use this value.
So in the second
plus
iteration, the values
2.532.
are, so you get minus 3.479
2.532.
and MBA you get it as
minus
plus 0.946.
So we will write the values here.
3.479 and minus 1.087.
So in the second
iteration,
now
the
we will
values
move
are
on to our third iteration. Okay, so third iteration
plus 2.532
RCB, R, that is R values
plus
and
0.946
capital MF remains the same.
minus 3.
The only changes in MBC. For MBC,
and minus
see, first two cases MBC you
1.087.
have to use. Now we
Minus
will move on to our third
3.479.
iteration. And for these two cases, for
Okay,
so
CB
third
you have to
iteration,
use
whatever you are getting
RCB
in this
R,
column, that is R values and
so in the third
MF,
iteration you
capital
get the value
MF
as,
remains
see,
the
you are,
same.
for MBC you
The
will be
only
using
changes in
minus
MBC. For MBC,
so you get the
first
value
two
as
cases MBC you have to use
minus 1.087
and for these two cases for
plus
MCB you have to use
2.68
whatever you are getting. Now in this for MBC, for these two,
so in the third
formula
iteration you
for
get
MCB,
the value as,
you have to use
you
the
are,
value
for
minus
MBC
1
you will be
point,
using
minus 3.479.
so you get the value as
minus 1.087 minus
plus
1.068.
so you get
Now for MBC,
plus
for these two
1.004
formula for MCB, you have to use the value minus 1 point. Sorry. Minus 1.0. You will get the value as,
so you get plus
1.0086. See, this should be closer to this. Okay. Otherwise, you can assume your answer is wrong.
Plus 2.686 plus
1.004
minus 3.538.
You will get the value
minus
as 1.105. Now
plus
you can write the third iteration.
See,
This should be closer to this. Okay. Iteration cycle. Otherwise, you can assume your answer is wrong.
Plus 2.686 plus
1.004
minus 3.538.
Here for
minus
MBC, 1.105. Now you can write the
3.538.
third iteration
For
in the
MBA,
Kanis
it is minus
iteration cycle.
1.105. So the values
Now we will
are,
move on to the fourth.
for the third iteration, plus 2.686.
Fourth cycle, fourth
plus
iteration.
1.004.
So fourth iteration for
Here for
MBC,
MBC,
small
it is
MBC, you
minus
have to use minus 3.538. Remains the same.
For MBA, it is
Okay,
minus
so we
1.
get
The value as
105.
minus.
Now we will move on to the fourth.
1.105. Sorry.
Fourth cycle, fourth iteration.
Plus
So fourth
2.
iteration for MBC,
707.
small MBC, you have to use minus 3.538.
1.012.
Now for these
so
two
we get
cases,
the value as
for
minus
MCB, you have to use plus
1.105. So
Sorry.
that you will get the value as minus 3.546
plus 2.
and minus
707.
1.107. You can continue the same procedure
1.012.
so that you get in the fifth iteration.
Now for
you
these
will get
two
the value
cases,
as
you have for MCB,
plus
you have to use
2.710.
710.
So that you will get the value
Plus
as
1.013.
minus 3.546 minus 3.547
and minus
1.107. You can
1.10.
continue the same procedure.
So you can stop with
so
this.
that you get in the fifth
If
iteration
you have
will get
time,
the value
if
as
you need more accuracy,
plus
you can go for
2.
more number of iterations.
710 plus
So increase the number of iterations, you will get more
minus
closer results.
3.547 and minus 1.10.
So I will write the values of
So you can
fourth
stop with
iteration
this.
and fifth iteration in the
If
Kanis
you have time,
cycle.
if you need more accuracy, you can go for more number
Fourth
of
iteration, the values are. So increase the number of iterations, you will get more
707
closer results.
plus 1.012.
Okay.
Here it is minus 3.
So I will write the values of fourth iteration and
minus
fifth iteration in the Kanis
and
cycle.
the last iteration, the values are
Fourth iteration, the values are
710 plus 1.0707 minus 3.547 and minus 1.10.
Now what you have obtained in the last
iteration, that is your and the last iteration,
okay,
the values
so
are
this is your small MBA, this is your small MBC, this is your small MCB, and this is your small
.013 minus 3.547 and minus 1.1.
Okay, so the rotational contributions.
Now what you have obtained,
we will write it as a step
iteration, that
6.
is your MBA. Okay, so this is your small MBA, this is your small MBC, this is your small MCB, and this is your small M.
So step 6. The rotational contributions.
So the rotational contributions.
We will write it as a step. So the rotational contributions are M MBA is equal to minus 1.018. MBC the rotational contributions minus 3.547. So the rotational contributions are plus 2.710 and MCD is equal to plus 1.013. Now we will calculate our end minus 1.018.
So final
end moments. MBC is equal to
that
minus
will be our step
3.547. MCB is
step
equal
7
to
is
plus
final
2.710 and MCD is equal to plus 1.013.
Final end moments, as I have told you
now
earlier,
we will calculate our end
it is an
extension of slope deflection equation.
Final end
So
moments.
MAB will be equal to
So that will be our step
MFAB plus, so step 7 is final end
2
EI by L into 2 theta A plus theta B.
So final end
So
moments,
this is nothing
as
but
I have told you earlier,
FAB. It
is an extension of
slope deflection equation. So MAB will be equal
plus
to MFAB.
So while writing
plus
the final end moments,
we will open a tabular column with EI by L into 2 theta A
so
plus
Mij
theta.
we have.
So this is nothing but
See MAB here it is 0, right?
plus 2
MAB
MAB
Since
plus
the
MBA.
ends are hinged.
So while writing
MAB
the final end
and
moments, we will open a
MBC
tabular
is
column
0.
with so the remaining things available are
Ij.
So MIJ we have MBC. See MAB here it is 0, right? And MABCD.
Since the
MAB and
ends are
MDC
hinged.
is 0. MAB and MDC is 0. So the remaining things available are MBA. End moments at A
MBC
and D is 0. That is MCD is AB is equal to 0 and MDC is equal to 0. AB. So we are not including these things here. 0. Remaining things available are MBA, MBC, MCB and MCD. MAB is equal to 0 and MDC end moments at A and D is 0. That is AB is equal to 0 and MDC is equal to 0. So we are not including these things that is here. Remaining things available are represented as I and B represented as G and MCD. Okay. MAB so now we will find right this, that is MFIJ. MFIJ, that is fixed end moment of AB, that is M. A so is represented as I and B is represented as J. In general is represented as I and B represented as J. So it is M. Okay. So now we will find right this, that is MFIJ. MFBA. Here I is B, F, J is J. That is fixed end moment. Fixed end moment we have AB. Determined in our first step. A is represented as I and B is represented as J. Is equal in general plus term, okay. 9. So it is now here I is B, J is C. It is nothing but end moment F for BC. MF BC here I is B, J is A. Minus so 2.4 end moment we have determined in our first equal to plus 3.6 end moment at B and M of CD is equal to minus 7.5 kilonewton meter. Now this is the first step. I is we are obtained from our first J step, is fixed end moment. So fixed end now moment we have to find what is 2 MAB. BC is equal so A is I, B is J. So we will minus 2.4 kilonewton meter. M of CB is equal to here I is 3.6 kilonewton meter and M of CD is equal to minus 7.5 kilonewton meter. This is the first step. We are obtained from our first step. I is C, J is now D. We have to find what is 2 MIJ. That is so A is I, B is J. So we will write MBA. MBA is minus 1.018. So 2 MBA so here I is 1.018 multiplied by 2 we get here I is B 2. J is C, 1, I is C, J is next, B, 2 M, I is B, C, J is D. Minus 3.547 multiplied by that 2 we get minus BA. 7.2 MBA. MBA is minus 1.018. So 2 MBA is minus 1.018 multiplied by 2 we get minus 2 plus 2.710 multiplied by 2 we get plus 5.420. DC. Minus 3.547 multiplied by 2 we get MCD. Minus 7.0 plus 1.013 multiplied by 2 we get plus 2.026. So next is MBA plus right? 2.710 multiplied by 2 we get A plus is I, B is J. So it is MJI. So MJI. MCD. That is M we get here plus you have to write 0.013 multiplied by 2 we get plus right? 2.0. So that is the meaning of this. So what is MAB? So next is MBA. Right? MAB is that is M we don't have, that is A 0. Is I, B is J. So it now is MJI. MCB so MJI plus 2.710. Here you have to write M AB is minus 3.547. Right? So that is the meaning of this. So what is MAB? So our final MAB is moments. We don't have, that is 0. End moments. Final end now moments. MCB. MIJ is equal to the summation of 2.710. That is MFIJ. MBC plus 2M minus 3.547. 2MIJ. Small MIJ plus 0. MJ. So our final, so adding moments. All the sum, we get end moments as final end moments plus 9 minus 2.216 plus 0 the summation of all these. That is MFij 4 kilonewton meter. MBC is minus 2.4 minus 7.094 plus 2.710. We get minus. So adding all these 6.784 kilonewton meter. Plus 9 minus 6 plus 5.6 plus 0 minus 3.567 we get plus 6.784 kilonewton meter. MBC is minus 7.4 minus 7.006 plus 2.710 we get minus 5.474 kilonewton meter. So these are 3.6 plus 5.420 minus 3.567 we get plus 5. Now last step we will find the simple beam moments, minus 7.5 plus 2.026 so plus step 0 we get is simple beam moments in order to draw the bending moment diagram. So these are our simple beam moments for the span AB. We have a UDL now last step we will find the simple beam moments, that is our step length of 6 meter. So our simple beam moment will be a parabola beam moment WL in order to draw the bending moment diagram. So we get simple beam moment 6 square divided by 8. We have a UDL of 2 kilonewton per meter for a distance of for the span length of 6 meter. So now our simple beam moment will be a parabola of WL square by 8. A 5 kilonewton load acting at a distance of 3 meter from B. 2 into 6 square divided by 8. So our simple beam moment will be the maximum concentration will be at 9 kilonewton where the concentrated load is acting, and it is W now for the span B by L. So we get 5 into 3 into 2 divided by 5 load acting at a distance of 3 meter from B. So it is a 6 kilonewton meter. 2 meter. And for our simple beam moment will be CD. The maximum concentration will be 8 kilonewton load acting where the concentrated load is acting 2.5 meter from and C it is W from A B by L. So it is we get 5 into 3 WL by divided by 5. Substitute A equal to L by 2, B equal to L by 2. So it is we get 8 into 5 divided and by 4. For the span we CD, get 10 kilonewton. We have a 8 kilonewton load acting at a distance of 2.5 meter from C and 2.5 meter from D. And then we will mark the final end moments. WL by 4. You can substitute A equal to L by 2, B equal to L by 2. We get 8 into 5 divided by 4. We get 10 kilonewton meter. So drawing the bending moment diagram. So first of all we will draw the simple beam moments and then we will mark this final. We will draw the simple beam moments first. We will draw the simple beam moments. Remember it is 9, 6, 10. So for AB it is a parabola. It is 9 kilonewton meter, right? So drawing the bending moment diagram at the midspan at the center midspan. For BC we will draw the simple kilonewton meter first. So 6 kilonewton is, so for AB it is a parabola where this concentrated load acts. It is 9 kilonewton meter, right? For CD it is 10 kilonewton meter at the center. 9 kilonewton meter at the midspan at the center. Now we will draw the final end moments. So at 6 kilonewton meter, at D it is 0 because they are kilonewton is at the place where this concentrated load acts. So it is a 6 kilonewton meter. For CD it is 10 kilonewton meter at the center of 6.784 minus 6.784. Now we will draw the final end moment. AB. So when you are considering the span HD it is 0 because they are hinged. For A it is 0. For B so the remaining so acting upwards. So 6.784. The final considering the span BC 6.784 minus 6.784. It is minus 6 anti-clockwise. So for the span AB it is plus so 5. When you are considering the span both are upward. AB so it is for A it is 0. For B A it is plus 4. So acting upwards 5.473. So 6.784. When you are considering the span BC for CD it is minus. BC Anti-clockwise
minus 6.
upwards.
Anti-clockwise
5.474.
CB it is plus 5.
And
Clockwise.
D it is
So
0.
both are upward.
Okay, so this is how.
So it is
So first
6
triangle like this.
784.
Then it is a trapezium. Then it is a
and
triangle like this.
5.47.
So now we will draw the
when you are considering
end
this
moment
moment
CD.
for CD it is minus.
So the end moments
Anti-clockwise
are
upwards
0,
5.474 and D it
6.784,
is
right?
0.
Okay, so this is how.
6.784
triangle like this.
kilonewton meter.
Then it is a trapezium. Then it is a triangle like this. So now we will draw the end moments. 6.784 to 5.4735. So the end moments are 0,
5.4735 kilonewton
right?
meter.
Then it is from
6.784 kilonewton
5.4735
meter
to 0. So then 6.784
So our net moment
to
is
5.4735.
negative
5.4735
kilonewton meter.
Then it is from
Negative
5.4735 to 0. So this is positive.
Negative. That means this is a sagging. Up to this
So
you will
our
have
net
a
moment
sagging
is
moment. Up to this we have a
negative.
hogging moment.
Sorry,
From
positive.
this to this we have a hogging
Negative.
moment. And from this to this we have
Negative.
a sagging moment.
Positive. So how will we draw the
this is positive.
deflection diagram? So this is our bending
Negative.
moment
That
diagram.
means this
We
is
will
a
draw the
sagging. Up
deflection
to this you
diagram
will
now.
have a sagging moment.
So
Up
this
to
is
this we
A,
have a hogging
B,
moment.
C.
From this to
and
this we
D.
have a hogging
So we
moment.
have
And from this to
point
this
of
we have a
contraflexion
sagging
at this
moment.
point. So how will we draw the deflection diagram? So this is our bending moment diagram. We will draw the deflection
Next
diagram
point
now.
of contraflexion at this point.
So
That
this
is plus
A,
2 minus,
B,
minus 2 plus.
C,
Plus 2
and
minus,
D.
again minus,
So
so
we
minus 2
have-
plus.
Okay, so we have only two
Point of contraflexion at this point.
So here it is a sagging. Then it comes to hogging. See here, then up
Next
from this
point
to
of
this.
contraflexion at this point.
See up to from
That
this
is plus
to
2
this
minus,
it is a sagging. From this
minus
to this
2
it
plus.
is plus 2 minus
Hogging.
again minus. So minus 2 plus. Okay, so we have only 2 points of
Now from this
contraflexion.
point to this point,
So here
again
it is a sagging. Okay, this is a sagging up to this.
Then it
From
comes
this
to
point
hogging.
this point.
See here, then
it is
up from
negative,
this
so
to
hogging.
this. See up to from this
again
to this it is a sagging. From this to
Sagging.
this it is
So this is our deflection
hogging.
diagram. Now from this point to this point again.
So
it
thank
is
you for
sagging.
today. We will see
Okay, this
next
is a
example in the
sagging up
next
to this.
class. Thank you.
From this point to this point, it is negative, so hogging. From this to this, again it is positive, it is sagging. So this is our deflection diagram.
So thank you for today. We will see next example in the next class. Thank you.